The medullary ischemic reflex is an autonomic reflex to a drop in perfusion of the brain. Now, of course, this is important. Look at the name, medullary, right? That sounds very brain-like. Ischemic, lack of blood flow. And not surprisingly, the brain has these mechanisms to try and to keep its blood flow going for itself. And what happens is the medulla monitors its own blood supply. And if there's insufficient perfusion, it basically goes to the cardiac centers and vasomotor centers and basically says, hey, I need more blood. And it does it by increasing heart rate and contraction force. So we already know that if we go back to our old equation, that cardiac output equals heart rate times stroke volume. You can see what we're doing is increasing contraction force will increase that, heart rate will increase that, and then the net effect is that I should get a significant increase in cardiac output as a result. And that should raise BP and hopefully restore normal perfusion to the brain. Not surprisingly, since we're talking about the brain, very complex, a lot of integration centers, a lot of feedback from different areas, is other things can affect the vasomotor center. Stress can do it, anger, arousal, not surprisingly, can also lead to an increase in BP. Now, there are a number of hormones, and we're not going to spend a whole lot of time on them, but they really influence things like blood pressure. Now, some act through vasoactive effects, and some of them act on basically regulating water balance. And we're just going to quickly look at some of these. Angiotensin II is a potent vasoconstrictor. Not surprisingly, that one of the big effects of that would be to increase blood pressure. Aldosterone, I'm just going to clear off some of this a bit. Aldosterone, so we're here at aldosterone, it promotes sodium. Now, I always think of sodium and water as being best buddies, where one goes, the other goes. So if I retain sodium, I'm going to retain water. If I try and get rid of sodium through things like the urine, water's going to go with it. They sort of follow each other like lost little puppies in many ways. And so aldosterone has an effect on sodium. And it increases blood volume. And of course, if I increase blood volume, I'm going to usually have an increase in pressure. Now, one way I always helps me remember what aldosterone is tied with. Now, it's a bit of a stretch here, is remember, it promotes sodium retention. And I always remember aldosterone. Now, it seems kind of weird, but oh well. Is aldosterone has sodium partially spelt backwards within it. So SOD of sodium. And that, for me, that's my mental reminder that aldosterone, with the first three letters of sodium, partially spelled backwards, and it is related to promotion of sodium. I don't know if that helps you. Works for me. Give it a try. The next one is ANP, atrial natriuretic peptide. Now look at the first word, atrial. That's starting to sound like heart stuff, and if you thought that, then you're right. It's released by the heart. We're not going to go in great detail, but what it does is it increases urinary sodium excretion. And remember what I said before, where sodium goes, who goes with it? Right? Where sodium goes, water goes. They kind of often travel together. They're kind of like best buddies. And that would reduce blood volume and promotes also vasodilation, which would have a similar effect. And all those together result in a lowering of BP. ADH, antidiuretic hormone. A diuretic is something that increases the volume of water in urine. So if it's antidiuretic, it does the opposite. It promotes water retention and raises BP. Now, with super high concentrations, pathologically high concentrations, it can actually also act as a vasoconstrictor. We also have epinephrine and norepinephrine. Now, they're an interesting one because even though it's the same chemical, this is a great example of how a receptor helps to determine in a given cell as to what the action will be. So in most blood vessels, I'm just going to clean this up a bit. In most blood vessels, it binds onto the alpha adrenergic receptors. And in those blood vessels, it acts in terms of vasoconstriction. In skeletal and cardiac, it binds onto the beta adrenergic receptors and end up with vasodilation. So that helps to explain why we can have two different effects with the same hormone basically being released. So what are the two purposes of the vasomotion? Well, it depends what you're trying to accomplish. If I get very localized vasomotion, I could reroute blood. If I do widespread vasomotion, number of blood vessels throughout many parts of the body, then basically I'm changing the total container size, which would change overall pressure. So it can be a general method of increasing or lowering BP throughout the body. Increase in BP requires things like the medullary vasomotor centers to be involved, or I end up with a widespread circulation of a hormone. It also is used, so this would be the case where I'm actually doing a lot of blood vessels, either dilating them or constricting them and changing the big total volume container size for all the blood. The other thing I can do is locally, let's say I have a blood vessel, and it bifurcates, okay? And let's say the blood's flowing in this direction, right? Some of the blood go here, some of the blood go there. Now we already know that one of the determinants as to whether blood's going to flow through something and how it's going to flow through it is basically diameter. So what would happen if, let's say this blood vessel really vasoconstricted? All of a sudden, its resistance has gone up significantly. And not surprisingly, yes, a little bit of blood will go here, but of course things like to follow the path of least resistance, and it will follow the low resistance blood vessel. So localized changes in blood vessel diameter can shunt blood from one location to the next. So as I said, we could have localized vasoconstriction. Specific artery constricts. The pressure downstream of the constriction point drops. The pressure upstream rises. It basically forces blood to go another way. Things like vigorous exercise dilate arteries in the lungs, hearts, and muscles. And with those dilated, they're now low resistance and encourages more blood to go there. Whereas vasoconstriction occurs in the kidneys and GI tract, so I'm less likely to send blood there. So by doing this localized vasoconstriction, it really gives me a lot of control over where I'm going to send blood. And here's this diagram that they're showing. Here's a gent, hanging out here watching, I don't know, his favorite Netflix show. Those legs haven't probably moved in a while, and I could almost guess that you get constricted blood vessels down here in the legs because the muscles aren't working. So there you go. Whereas if you're out playing soccer, you're running around, and you see that the blood vessels open wide to basically shunt blood down to the muscles. So this happens all the time in the body. And just to have a quick look, and what we're looking at here is the distribution. Now, I never ask you to memorize these numbers, but just give you an illustration. Here is sort of a pie chart of the distribution of blood, and we're talking about at rest versus moderate exercise. And you can see there's a real shift in where blood goes. At rest, a small bit to the muscles. GI gets a fair bit. Renals, your kidney, cerebellum, right? Or cerebral, I should say, etc., etc. Now look at the shift that we have here. That over here on the right, we can see that more blood gets shunted here. So the muscles get a lot of the blood. So who's going to give up blood? I'm not going to create new blood. I'm just going to reroute it. Well, not surprising. Look at GI. Here's GI at rest. Here's GI at exercise. That's quite much smaller. Also, look at renal. Renal, very, very large here. 22% of basically cardiac output ends up in the renal system. Here we're down to about 3.4. So it's a good illustration of how we get this shifting. Okay, we're going to end there. That was a pretty long one. And what we'll do is we'll start the next video talking about capillary exchange.